Yeah, my name's Matt. I'm from Norway, and I'm responsible for Norway's knowledge base for climate adaptation in the coastal zone. And it's hugely, I'm really happy to be part of this. I think it's hugely beneficial, this European exchange. So I'm really happy that Norway's contributing and also learning as part of this initiative. And thank you to the organizers. So the session we're doing now is sea level rise more than one global number. And it's more than one global number because we know that sea level rise is governed by many different processes, and those processes cause sea level rise or changes over different spatial scales and over different time scales. We know that there are considerable uncertainties related to sea level rise. And so this session, we're really kind of drilling down into the physical science of sea level change, sea level rise. And we're going to be covering everything from the global mean. We're going to be looking at extremes. We're going to be looking at long-term sea level rise and past sea level rise. So it's very exciting. I think we're going to be covering a lot of stuff. And we have, as was said, we've got 3 keynote speakers I'm very happy about. And then after which, we're going to have a panel discussion with the opportunity of questions and answers. But after each speaker, you also have a chance to come with questions. And please do, please come up to the microphones or send your questions in online. So our first presentation today, we're running slightly behind schedule, but each speaker has around 12 minutes, some of them 3 minutes for questions. We'll try and stick to that. Is Roderik van der Waal. He will be talking about what is a reasonable high-end estimate and how to get there. Roderik is from Utrecht University. He's a professor in sea level change. He works on various aspects of sea level science, varying from the development of ice sheet models to assessing sea level information relevant for stakeholders. And he's also the co-leader of the Knowledge Hub on Sea Level Rise task group on the physical science. So in your own time, Roderik, thank you very much.
Okay, thank you very much for the introduction. I will give a presentation on behalf of many people on this topic. And you see here all those people who are involved. It's what I call the WCRP Grand Challenge team. And these are about 30 people who have been working over a period of 2 years on trying to get a high-end number for sea level rise. And with high-end, just to prevent any confusion, with high-end I mean a high-end in the trend, so it's not an extreme value. The traditional way to look at sea level rise projections is to consider the likely range. And of course, from a stakeholder perspective, there's also a strong need to get information which is outside the likely range, as we framed it in SROC, or high-end, as we frame it here, or in some cases also called the worst case scenario for sea level rise. And here on purpose we call it high-end. And an attempt for a definition of a high-end, I think, could be that a high-end sea level projection uses multiple lines of evidence and physical plausibility to constrain the estimate of critical processes contributing to sea level rise. And in red, I think there are 2 very important words: multiple lines of evidence and physical-based plausibility. And, well, that is the key, I think, and that means that, per definition, this number, or it turns out to be a range, will not have a fixed probability, and that's a little bit a difficulty for some people, but I think we are not, from a physical point of view, not sure enough about to assign this to a very specific probability number. But nevertheless, I think it's useful to have this range. So this is much more about how much sea level rise and when. So what are the challenges to get to this? And there are various ways how you can come to projections of a high-end value for sea level rise in future. And from a physical point of view, the most desirable way to do this would be with an Earth system model, But Earth system models do not have explicit ice components. They have output which you can use to force an ice sheet model, but it's not the sea level is not the outcome of a typical IPCC model. So this is a shortcoming, and we will overcome this in years, and that's what we said 10 years ago as well. So this may take another 10 years before we are there, I think. So the alternative approach would be what they typically did in AR5, deterministic ice sheet models which were forced with the output of IPCC style models. And well, that works to some extent, but the physics of ice is poorly understood, and that makes it very difficult. So another approach could be a probabilistic approach to get to a high-end sea level. That was attempted some 5 years ago, explored, but then they often have an Antarctic contribution which is based on a specific study, and that makes that it's in fact not really a probabilistic approach. Another alternative which has been explored is the use of structured expert judgments, and the most famous one is the paper from Jonathan Bamber, 2019, but there it's questioned whether the outcome depends on the experts, and you never know what the experts have precisely in mind. So all in all, by stakeholders, this is often considered to be not very transparent, and for that reason not the ideal way to get to a high-end number. And in the old days, we had a first attempt, I would say, to use kinematic constraints on ice flow to get a high-end value of sea level rise. So in fact, there is not a real single approach which gives the unique answer. So it's not very easy to get there, I think. And alternatives are, in a way, proposed a couple of years ago by Ted Shepard, who suggested to work more with what they call a storyline approach. And that's then the identification of physical self-consistent plausible pathways. So it's more moving from what will happen to what is the impact of. And this idea has been explored, for instance, in the IPCC report with what I call an high impact, low likelihood scenario, a hill scenario, which is shown in this figure, which you hopefully know because it's from the latest IPCC report. It's an explicit approach, but it also has some limitation. It's a limited assessment of the literature, and it uses not really this multiple lines of evidence, but it uses single lines of evidence to get to a high-end estimate of sea level rise. So it's probably not the most ideal case either. So what we try to do in our approach is we started to work from the physical reasoning, particularly of the glacier and ice components, because the ocean component can be resolved by Earth system models, so you can take it from there. It's a large spread of models, so that's probably giving a good idea on the tails of the distribution, but for the ice component this doesn't work. So the physical reasoning for glaciers is expressed here, where you see that in fact the temperature change and the precipitation change are both driving the changes in the surface mass balance, which in the end then contributes to sea level rise. In practice, it turns out to be very strongly driven by temperature change. So the uncertainty is limited because the temperature change, even on a local scale where all those glaciers are, is reasonably well projected. For Greenland, this already gets much more complicated, and the reason for that is that there are more processes, physical processes, which are relevant to estimate the contribution of the Greenland ice sheet. We are very unsure on the evolution of the albedo, which is the amount of the reflection of the sunlight, so whether you have more or less absorption of energy and how that evolves over time. That's an uncertain process. You have dynamical problems in the sense that if there are preferred atmospheric systems which will appear more often in future than what is captured by the Earth system models, then you may have a different contribution of the Greenland ice sheet than what is in the standard projections. So the uncertainties on the Greenland component are much larger than on the glacier component, and they focus essentially around trying to get a good projection of the surface mass balance, because this surface mass balance drives the dynamics and it drives the outlets and then eventually the sea level rise. But there are more uncertainties than for the glacier component. And the high-end estimates we make, we do that for two different scenarios. A high-end scenario, SSP 5 8.5, and a low-end scenario, SSP 1 2.6, and we do it on 2 time scales. And if you do that, you can see that on the different squares of this table, you get different processes which are relevant to get to a high-end estimate. So the SSP 1 2.6, 2100, that's the simple one where you don't have very strange processes playing a role. It's mainly temperature increase which drives, so it's a bit like for the glaciers. But if you look to the longer term perspective, then you have to take albedo feedbacks into account, atmospheric circulation changes, possibilities for tipping points in the system. So you have to take much more physical processes into account, and that of course introduces much more uncertainty. So any high-end estimate depends on scenario and it depends on time scale. For Antarctica, it's even getting much more complicated because our physical understanding of ice in Antarctica is less good than for Greenland. And the main reason, in fact, is that you also have to take into account the ocean-ice interaction in Antarctica, because many places of Antarctica, the Southern Ocean, is in contact with the ice. And that ice is then what we call ice shelves. They are floating parts around the Antarctic ice sheet. And they're extremely important because they protect the ice sheet, they keep the ice sheet in place. The ice shelf melt will not immediately lead to sea level rise, but as soon as these ice shelves are gone, then the ice sheet will contribute larger to sea level rise. So it's very important to keep track on ice shelf breakup. And once the ice shelves are broken up, then all these complicated dynamical processes like marine ice sheet instability and marine ice cliff instability, they contribute to the fact that the Antarctic ice sheet will get smaller in future. So probably the most critical process for the coming century is whether the large ice shelves will break up or not. And then one other aspect to get to a high end is that you have to combine the different ice components to each other. And this is often an overlooked item, I would say. But it's not necessarily true that if the Antarctic contribution to sea level rise is high, that the Greenland contribution is also high. And the reason for that is that the climate change is not identical in the southern and the northern hemisphere, but also, as I explained previously, the different processes are very different, which control the high-end numbers for Greenland and Antarctica. So somehow we have to make considerations on whether the two contributions are correlated or not correlated to each other to get to a high-end number. And that is an important aspect on which we are very uncertain, I think. And that means that any high-end estimate is in fact a high-end range, because you have to make assumption on what we call the covariance between the components in Greenland and Antarctica. And that makes a difference in whether you get to a certain value. And here you see then in the end the high-end scenarios, which I call the help scenarios, because what I did not mention explicitly so far is that this has been about 7 or 8 people of this 30. They are part of what I would call the stakeholder community. So this is a kind of co-creation. And therefore I thought maybe we should call this help scenarios. Anyhow, you see that we end up with numbers which are not the same as the IPCC numbers for some scenarios and some timescales, but also still considerably high numbers, which call for action, I think. So if we compare what we did with what was done in the AR6 report, which is probably the most recent and well-known alternative for a high-end scenario. We see that for the near term, which I call near term 2100, a low scenario, we get more or less the same results. So there's not too much of a discrepancy for those timescales and those scenarios. But as soon as you start to look to the high-end scenarios, even on the reasonably short timescale there, you see quite big difference already with the IPCC results, which are then in this case for the 2100 plus 5 scenario related to the difference in estimates for the Greenland ice sheet. And on the longer term timescale, 2300, which is maybe less relevant for adaptation but important for mitigation purposes, the differences start to appear close to different estimates for the Antarctic ice sheet. But they are very high anyhow. So in conclusion, I think we offer hereby an alternative, transparent, physically based approach using indeed multiple lines of evidence and thereby, per definition, of greater practitioner value according to our stakeholders. And that leads to large differences in adaptation efforts between 2+2 and +5. I think that will be clear for everybody in the room here. And beyond 2100, you see that you get very different results for the high-end estimate depending on the scenario, which is a call for mitigation, I would say. And in contrast, you also see that if as society we manage to keep climate change limited to 2 degrees, we will see that adaptation remains feasible at many places beyond 2100. So there's often a paradigm where it's argued that sea level rise might be up to 2 meters in 2100, and I think on the global scale this is extremely unlikely. It's above our high-end estimate, significantly above. But on a local scale, this cannot be excluded, I think. And of course, a next step would be to translate this high-end global values to local values, as we already heard in one of the previous talks, that is, of course, a much more relevant quantity. And maybe we should repeat this every 5 years.
Thank you very much, Roderik. You've run exactly to 15 minutes, but I think we have time for a very quick question. Anyone would like to ask a question? Please stand up. Tell us who you are when you come up to the mic. And
I'm here, Institute of Marine Science in Venice. I was just, if you can add a comment to this last sentence about locally. I mean, we are dealing mostly with global, but also we do need local. But why we should expect more probable of such a value on the local scale with respect to the global?
Well, there are various aspects, various processes which make that differences on the local scale may be up to 20–30% compared to the global number, related to where you are relative to ice sheets. The further you are away, in the worse value you get, and also the local ocean component may vary from place to place. So these are the physical mechanisms which drives that you can get values which are 25% higher than the global mean value. And they need to be calculated separately. We did not do that here, but in principle the tools are there to do that.
very good. Thank you, Roderik. I'm sure there will be other questions for Roderik, and he will be coming back after the panel discussion, so you can ask him then. Okay, our next speaker, Angélique Melet, will be speaking about how to get from global to local projections of sea level changes. Angélique is a physical oceanographer who specializes in sea level changes with a focus on the coasts. She contributes to the development of climate services dealing with sea level changes and related risks, and is a co-leader of the Knowledge Hub on Sea Level Rise Task Group on Physical Science, and she works at Mercator Ocean International. think that's all I'll say there. There's more to say, but please come up, Angélique.
Thank you, Matt, and good morning, everyone. So in this presentation, we will gradually move away from the global mean sea level rise that we've been hearing of, and we will move towards regional sea level changes. And we will also see how we can refine the regional sea level changes projection that are provided by global climate models to get information on more coastal scales, which is needed for adaptation. So first, the drivers of global, regional, and local sea level changes are numerous, and they also involve diverse components of the climate system. And this is synthesized on this figure where you can see the global drivers in blue, the regional ones in yellow, and the ice processes that Roderik has been talking about in purple. And I will go through them in those slides. So the global mean sea level rise is mostly driven by the thermal expansion of the warming ocean, but also by the transfer of water mass from land to the ocean, and this can be ice or liquid water. And this is caused by melting mountain glaciers, the ice sheets, Greenland and Antarctica, and also changes, to a lesser extent, changes in the land water storage because of water impoundment on land or because of water pumping in the aquifers. And the contribution of all those processes are shown here sorry. No, it doesn't. Yeah, it does work. Yeah, are shown on this figure for the different components during the 21st century. And all those processes are taken into account in IPCC reports, as you can see from the latest report, with the projected global mean sea level rise considering different climate change and socioeconomic scenarios until the mid-22nd century. Now, regional departure from global mean values are mostly driven by ocean dynamics due to the redistribution of heat, salt, and mass in the ocean by ocean circulation, but also by the transfer of mass from land to the ocean, which induce currently changes in Earth gravity field, in Earth rotation, but also deform the solid Earth. And that leads to regional patterns of sea level changes, especially at high latitudes and with larger contribution in the tropics. In addition, the solid Earth is still adjusting to the last deglaciation, which started 20,000 years ago and ended about 8,000 years ago, and that induces a vertical land motion that needs to be considered when we are thinking about relative sea level rise, so relative to the ground where we live, basically. When combined all together, those processes provide what we call the time mean sea level at regional scales of hundreds of kilometers, and this is also provided in IPCC report. You can see here the regional sea level change at 2100 for different scenarios, and as explained by Roderik, regional departure from global mean values can reach something like plus or minus 30% at those regional scales. And although I'm focusing here on projections for the 21st century, it should be highlighted that the spatial heterogeneity of sea level rise has also been observed thanks to tide gauges at the coast, but also thanks to spatial altimetry on the open ocean. But of course, the impact of sea level rise is occurring at the coast. And when we think about coastal sea level, we need to consider both the time mean sea level change at the coast, but also extreme sea levels. And to get those, we need to combine the time mean sea level that I've presented before with additional coastal processes. And for extreme sea levels, those are including astronomical tides, storm surges, wave contributions that are shown here in red in this figure. And actually, those processes are not yet included in global climate models. And to add a little bit of complexity on top of all of that, those coastal drivers can also interact together in many ways, and this is shown here. And this can lead to substantial changes in sea level, especially during extremes. There are also other processes that contribute to coastal sea level changes, such as river runoff, seiches, on more local scale even. There are also local vertical land motion that are very important. And you can see here for Europe that there are actually areas that are largely being uplifted, and this is the case for Scandinavia, and this is in response to the glacial isostatic adjustment mostly. But there are also some places that are largely subsiding, and you can see that Venice is one of those places, and it's usually because of non-climatic factors, human intervention, such as groundwater extraction, for instance. Now, this is what we get so far, and this is what you find also in the IPCC reports. But if you want to also refine the global regional sea level change projections that I've shown before to get more local, more information on more coastal scales, let's say, there are different methodologies that can be used. One of them is to use hydrodynamic models, and those are useful to refine the resolution, especially in coastal zones. And this is highlighted in this figure, where you can see the refined resolution as you get closer to the coast in a fjord area in Norway. Those models are often used to model tides and surges, and as such, they are 2D models. They ignore ocean dynamics, but you can also add sea level in those models and produce estimates of the changes in extreme events on broad regional scales, because they are fast in terms of computational time. And this is shown here with the change in meter of the 1 in 10 year return level for the end of the century along the global coastline. Another method that can be used to refine information at the coastal scale is to perform what we call a dynamical downscaling, so basically a zoom on a given region. And to do that, you need to implement a regional model that is similar in kind to climate models and are actually forced by them, but they have a higher resolution. And one thing that is interesting with those models is that the physics can be adapted to the region. There is also the possibility to implement such models to leverage on regional ocean and wave systems that are currently used in operational centers. And such dynamically downscaled models for sea level changes are being developed over different parts of Europe, such as the Mediterranean Sea, European Northwest Shelf, Northeastern Atlantic, but also other regions around the world, and the list is not exhaustive here. Dynamical downscaling for sea level changes is also being further developed for European regional seas in European projects, such as Coquelicot. So to better highlight the benefits of going to higher resolution there, I'm just showing here the bathymetry for different models at different resolution. And you can see one model that has a 100-kilometer resolution, so this is typical of CEMIP model, and you can see the bathymetry in this model. The bathymetry is the ocean bottom topography. And you can see that in this peculiar model, the English channel doesn't exist. You do get also higher resolution climate models, and you see that the improvement that you get when you are moving to a 50-kilometer resolution model, but you see still the step change that you can get when you go to even higher resolution, such as 7-kilometer resolution here, with a regional system dedicated to this area. Another very interesting advantage of dynamical downscaling is that you can actually include more processes than what is including in global climate models. And of interest here are, of course, processes that are relevant for coastal sea level changes and extremes. And this is being implemented over the northeastern Europe. We have an ocean component in this system that both models mean sea level changes, such as in global climate models, but at higher resolution, as shown in the picture. But it also models at the same time tides and storm surges and the interactions between those processes. The system also comes with a wave component and to model the wave setup contribution to extremes. And it's actually forced by sea levels and surface currents so that you capture, at least partly, the interactions between all those drivers. And such a system can be interesting as well to inform on uncertainties and on the importance of processes that are usually not taken into account when we are studying projected changes in extreme sea levels, such as nonlinear interactions between wave and sea level. And I will illustrate that in this slide, where you can see that this can play a role in microtidal areas, such as the Bay of Mont-Saint-Michel in France. And this is illustrated with a figure where you can see the hourly sea level changes in gray, the significant wave height when you do not account for nonlinear interactions between wave and sea level in red, and when you do in yellow. And you see that when you account for those interactions, you modulate the significant wave height with the water level, basically, and you get as well a larger significant wave height during the extreme event. And significant wave height is actually a key parameter to estimate wave setup contribution to extreme events. However, wave setup has not been typically included in studies of projected changes in extreme events because first, it's very difficult to estimate web setup changes on broad spatial scale. This is a very uncertain contribution. And also most of the studies studying projected changes in extreme levels are based on tie gauges. And tie gauges, although they are very interesting data records for sure, they do not or only partially capture web setup. But anyway, with such a system, we can just highlight that if you include web setup, there is the possibility to really change the statistical distribution of extremes. And this is shown in those curves of return levels for 2 areas in France. And you see the curves, the return level curves, when you do not include for web setup in black, and when you do in red and yellow. And you see that you get different distributions and higher amplitude events. And I would just like to say also that this can have an implication for the amplification of historical sentinel event, amplification of extreme event, and how often they will occur in the future. And okay, and you can see I'm almost finished. And you will see in that slide that actually when you include for web setup, you tend to delay in the future the year at which your historical sentinel event, which has a return period of 100 years, will occur on an annual basis, so every year in the future. And there can be like a substantial delay when you include for web setup in this timing, actually. And that can have implication for adaptation. All right, so to conclude on this presentation, there are many processes that are driving sea level changes at the global, regional, and coastal scales. So that makes it challenging, but also exciting to model coastal sea level changes needed for impact studies and adaptation. And I think that with that, you saw that sea level rise is certainly much more than a single global number. There are different methods that exist to refine regional sea level projections that are provided by global climate models to get more coastal information, although it might not be yet at the very local scale, so still kind of regional information because of the resolution of models. I would like to stress as well that there are many things that we know about sea level rise and sea level changes, and that is highlighted in IPCC reports with the likely range, etc. But there are also still uncertainties in different processes, such as in the ice sheets. And those uncertainties are cascading towards the local scale as well, and amplifying at the local scale. There are still processes for those coastal changes, especially for extreme events, that need to be better characterized because we still have low confidence in such processes. And I will stop here. Thank you.
Thank you very much, Angélique. That was 12 minutes and 10 seconds, so you timed that impeccably.
I was fast, I guess.
We have a few minutes, therefore, for questions, even though we are running a little bit behind schedule. Does anyone want to come up to the microphone, or do we have anything on the online questions? We also have the opportunity to question Angélique when she comes back for the panel discussion. In which case, oh, okay, yeah, we have a question, yes. Do you want to have the microphone here?
Thank you, Angélique. Very important. Just if you can overview to us the unknown couplings between waves and the currents that we have still to insert when we do wave coupling, wave and current coupling for coastal inundation. Are there issues that are still to be clarified?
Yes. Well, yes, certainly. So I think in terms of wave and currents, especially you said coupling, those were, like, they can play a role for refraction of waves. They can change a little bit the wave key parameters that are needed to estimate, again, the wave setup or the wave run-up. And those are not necessarily taken into account. I do not even have a study in mind, actually, where this is accounted for, I think. But again, if you do that at the regional scale, there are different models that exist that are including this coupling, and you could infer some uncertainty from that, I guess, yeah.
Thank you, Angélique. I think we're going to have to move on, but hold on to your question, and we can come back to it when we get to the Q&A at the end. Okay. Thank you very much. Our next speaker is Michalis Vousdoukas. He's going to be talking about what extremes to expect Michalis is a coastal oceanographer currently employed at the European Commission's Joint Research Centre. He is part of a group carrying out multidisciplinary work, developing tools and methodologies allowing to assess climate change impacts along the European and global coastlines. I'll leave it at that and take it away, Michalis. Thank you. 12 minutes.
Thank you very much for the introduction. I work for the Joint Research Center. This is like the in-house research institute of the Commission. We are a group of people that we are working on different natural hazards, and I'm leading the group that works on coastal flooding. So here, let's say my main collaborators. So when we're talking about coastal risks, we know that climate is going to change different hazard components, and we have in the GRC people that are working in different natural hazards. And we know that the climate is going to affect also river floods, heat waves, droughts, wildfires. Coastal flooding has a particular characteristic, which is sea level rise, which results in this acceleration of the extreme events that other people also discussed before. So this is acting like a magnifying factor, and it renders coastal flooding one of the most dominant natural hazards in the future. So, for example, my colleagues, they have calculated that right now, river flooding accounts for 0.04% of Europe's GDP. In the future, this is going to go to 0.1% according to projections. Coastal flooding is like 4 times less important than river floods, but in the future, it's projected to become 3 to 9 times more important than river flooding because of this sea level rise accelerating effect. So let's say 6 years ago, we started building what we call LISCOs, which is like a framework of a set of different tools. We use existing data of sea level rise. We do projections of waves, storm surges. We do inundation modeling. We started at European scales, and we also do at global scales. We also try to use the best information to calculate impacts. So we try to use gridded projections of socioeconomic parameters. We try to provide information which is useful for policymakers. So when we are talking about coastal flooding, of course we have sea level rise, and already people gave a lot of information. But the most important thing is that we have constructed a lot of things in the coastline, because if there was no human presence, climate change, sea level rise would be no problem. So we have this dramatic increase in population. Projections give that population is going to continue rising. Many of these people are on the coast. Most of the trends is that people are going to move to cities, and they are going to move to the coastline, and this is what makes sea level rise a problem. Here I give a very example of one of our first important studies, projections of extreme sea levels. So how the combination of sea level rise, changes in tides, changes in waves, changes in storm surges would affect the extreme sea levels. And for different scenarios, so you can see RCP 4.5, 8.5, and we project increases in the 100-year event between 20 to 30 centimeters by 2050 and 51 to 86 centimeters by the end of the century, talking about the median values. Then comes this figure about the change in the frequency that also Nadia showed. And I mean, the truth is that from an engineering perspective, where engineers always think about return periods, and everything that we construct on the coast is designed for specific return periods, such an acceleration it's a bit dramatic. So the red means that what we have now, the event that happens once a century will happen once a year, and this is already the case from 2050 for many places in the world. Now, such an acceleration of the frequency of extreme events means also acceleration, means also increase in the impacts that we are going to expect. So here we have expected annual damage and expected annual number of people affected during the century under different scenarios for Europe. And we are talking about, we have an estimated expected annual damage of a little bit higher than 1 billion. And we project that this can increase even by 2 or 3 orders of magnitude, depending on the scenario. Of course, this has to do with the coupling not only of the sea level, of the physical changes, but also the coupling also with the socioeconomic projections, which is a bit of, it's important to consider. The other things that we found is that we know that until now the consensus is that studies that were reporting an increase in risks, but this increase was mostly due to socioeconomic change. So we were constructing more on the coast, there were more assets exposed, and we had an increase in risks, even though mortality was decreasing because there were better informed societies, better early warning systems. What we saw in our projections, and you can see it here in the, for example, this would be the future impacts as a percentage of the GDP, only driven due to physical changes, only due to climate change. And here is the increase only due to socioeconomic change. You can see that physical changes become the main drivers of the increase in future risks. And this is the combined event effect, and you can see that also it's non-linear interaction. So this is a deviation from what was happening until now. Now here I saw results from a cost-benefit analysis about protecting the coast. So the color expresses basically for every euro we spend for protection at NATS2 level, how much money we save. So this is an analysis which is done at segment level every 25 kilometers. And you can see that, for example, when you have blue, it means that for every euro we spend, we will get 10 times more, we will avoid more losses. Now, what is interesting in this study is that we find also that in most of the European coastline, it's not beneficially, it doesn't make sense to adapt, at least in economic sense. It makes sense to adapt only where we have the human development, large cities, etc. And this is the minority of the European coastline. This is the same results at country level. So you can see here present protection economically optimal for at least 77% of the European coastline. But the thing is that at places where we have urbanization, this cost-benefit, this benefit to cost ratio become like 100 or 1,000. So it's by far, we have by far motivation, economic motivation to protect. And here you see also the uncertainties. It's interesting, for example, the Netherlands come with this high uncertainty because it's already a very protected coastline. So in most of the cases, we will have no flooding. This is done with probabilistic scenarios, Monte Carlo simulations. So we have like thousands of ensembles, and for most of them, there is no flood. But when there is one flood, then we have massive losses. Going globally, these are results from a recent paper where we did about projections of coastal erosion. And we found that a big percentage of the world's sandy beaches will experience shoreline retreat, which exceeds 50 meters, and this means that several of them will not have the capacity to sustain such coastal retreat. I'm also checking my time here. Okay, I have still 3 minutes. And we also calculate the uncertainty. What is funny about coastal erosion is that we are talking about natural processes, but already most of the world's shoreline is artificially managed. So we are not talking about the natural environment anymore, and this is quite a deviation of what at least I had in mind when I started to study geomorphology. Then another recent work that we did about natural heritage. So this is about African natural heritage. It was part also of the IPCC recently. We did erosion and flood risk assessment in different natural heritage sites, and 2,084 in total. And we found that 56, they are already under risk from erosion and flooding. So this is another part of the coin. Let's say Europe, which rich, developed coastline, where most of the places are well protected, at least for the time being. But in other areas, people are already experiencing risk. And in the future, at 3 times more African heritage sites will be exposed to flooding. And this is another thing about mitigation, is that in all our studies we see that mitigation will reduces by between 20 and 50% of the expected losses. So in all our studies we find very strong motivation for greenhouse gas emission mitigation. And the last slide, it's a study that is now under review. So it's a risk assessment about small island developing states. So we try to do a global assessment of the impacts of climate change in all small island developing states. So these are the little islands, remote, where there will be a lot of challenges because these places, they are already fragile economies, very dependent on tourism. It's difficult for them to adapt also, because even if you want to do beach nourishment, to construct something, you don't have resources nearby, you have to bring them from far away. And we also see that we have 5 times increase of the expected annual damage for a high emission scenario, which translates to 20-fold increase as a percentage of the GDP. And again, and these studies, they are also considering global warming levels. And we see that even if the 2 degrees warming we succeed to keep the warming below 2 degrees, we will still have a lot of impacts in these areas which are not sustainable. So something has to be. It's an early warning signal, let's say. Thank you very much.
Thank you, Michalis. We have a few minutes of questions. So I can ask a very quick one, and you covered a lot of different things there. What specifically for Europe, projections of the extremes, what are they telling us about what's going to happen in Europe in the future? Can you say something on that?
Well, I think that the big problem is in the Mediterranean Sea, because when you have an exposed oceanic coastline, you already expect waves, 5-meter waves, or even 20-meter waves in Portugal, let's say. You have tide, which can be 2 meters, 3 meters. So there, 30 centimeters of sea level rise, or half a meter, or even 80 centimeters, it's just a small percentage of your extreme sea level. And whereas in the Mediterranean, maybe your storm is 1 meter and you're going to get half a meter of sea level rise, and this changes completely how the things will work. For example, I come from Greece. We're used to have the restaurant with the tables right next to the water, put our feet in the sand while we eat. This is not possible yes, I think this is the Mediterranean is going to be the main battlefield, let's say.
Thank you very much. Do we have another question from Michalis? Please come up to the microphone and introduce yourself and then ask your question.
Hi, thanks for the presentation. Christian Ferrin from ISMAR. I was just wondering, even on the Mediterranean or European level, if the increase in extreme sea level is mostly due to sea level rise, or there are also changes in the meteorological component of the extreme sea level?
Well, in our projections, we see that the change in the meteorological extremes, they are not so strong. For example, in the area of the Basque Country, around Cadiz, in Portugal, the South Atlantic, the signal is very weak. But at some locations, we find that the increase in the meteorological component can reach up to 30% of the sea level rise. So there are already some studies that they show that meteorological signal is already accelerating erosion, some studies from American colleagues. So I think that after 2050, the sea level rise will obscure the changes in the meteorological tide, unless we have some tipping points and the climate starts to get crazy and things change.
Thank you. Perfect. Okay. We've finished with our keynote speakers now, and we're going to move on to the panel discussion. Michalis, don't go anywhere, because you can come and sit up here, I think.
Get my tea.
Yes, get your tea, yes. So can I ask those 4 panelists to come up? And then also we need I think our keynote speakers can also come up at the same time, because they will be able to contribute to the discussion afterwards and answer any more questions that you might have. All right, let's see how this goes. So what we're going to... we've got Jason as well. Very good. So we've got 4 panelists here today, and how this is going to work is I'm going to ask each of them a question in turn. They're going to have around 5 minutes or less to expand on that question, and then we're going to try and get then we're going to open up a bit more from more general Q&A. People can come up to the microphones, people can send in questions online, and we're going to get a bit of a debate here. And the purpose of this is to kind of make that bridge between the science and the stakeholders. So we're going to touch on the physical science, but we're also going to touch on things like climate services, interpreting data, and these other things. So, shall I make a start and ask my first question? All you have to do is when I ask you a question in front of you on the microphone, you just need to press the green button so the red light comes on, so that when you can speak. So I'm going to start with the person closest to me, and that is Marta Marcos. And the question I have for you, Marta, is could you tell us about, rather, the main observational data sets in looking at sea level, and what they tell us about sea level in Europe and the different basins across Europe. Just remember, just to introduce yourself very quickly before you answer that question. Thank you very much.
Okay, thank you, Matt. Yes, my name is Marta Marcos. I'm working at the Mediterranean Institute for Advanced Studies, based in Mallorca. I'm also associate professor at the Department of Physics of the University of the Balearic Islands, and I've been working on sea level issues from mean sea level to extremes during the last almost 20 years already. So about the main observational data sets, many of you know that there are 2 main observations from sea level. We have satellite altimetry since almost 30 years ago, which is covering most of the global ocean and providing very relevant information on mostly mean sea level changes in the open ocean with high accuracy and also close to the coast. We also have the tide gauges. The tide gauges are among the oldest geophysical records because they are very relevant for maritime navigation purposes. So the first measurements date back to the 17th, 18th centuries to improve our knowledge on tides mostly. So for climate studies, when we think about climate studies, we want to have something that is really very long, centennial scale. So the information on sea level provided by the tide gauge records is very valuable. Also, not only for mean sea level, also for extremes that we have been discussing here today, because the tide gauges, in contrast to satellite altimetry, they are recording sea level in a continuous way. So that means that we have very high frequency samplings, and we can also have information on tides and on extremes. But of course, tide gauges are not without problems. First of all, they are sparse in space. So in contrast again with satellite altimetry, we don't have a nearly global coverage, only at some local points along the coastlines. And it is very important for climate studies that the records are consistent vertically. That means that they have to be referenced to a benchmark. And if the tide gauge changes its side, or we change the instrument, they have to be vertically referenced. And another issue that we have to keep in mind with tide gauges is that they are measuring relative sea level instead of absolute sea level. So that means that we have information of both vertical land motion and the ocean signal. So if we want to understand the ocean signal, then we need a way to remove this component of vertical land motion, which is fortunately achievable nowadays, partly because of the solid Earth models, but also because in situ measurements of, for example, GNSS data. So where we can get these data sets? Well, fortunately, this is freely available to the scientific community and to the stakeholder community. We know that we can get the gridded data and along track data from satellite altimetry. For example, from the Siemens service, Copernicus is providing that on nearly real time in research quality. And also we have several international databases for the tide gauges that can be reached easily from anyone. If we think about mean sea level, perhaps the best known service is the permanent service for mean sea level that is based in Liverpool and has been running for more than 80 years now. And there are about 2,000 tide gauge stations with monthly and annual mean sea level with a subset that has, it has also information on the vertical referencing. If we are more interested in extremes, there are several other databases. One, perhaps the most complete, is the GESLA, Global Extreme Sea Level Analysis dataset, with several thousands of stations that have been compiled from all national, international, and regional services that provide freely available high-frequency sea level data. And by high frequency here, I mean hourly and above that. One has to be careful when using this database because this is a compilation of all the stations that have been made available through different services. And some stations are duplicated because the provider is publishing these observations in different databases. So, and also, they can be duplicated with different research, different quality controls. And then there are some others. For example, last year was published a new database of sea level, very high frequency sea level, called MISELA. This was done by some researchers of the University of Split. And this is a very, very high frequency data of the order of minutes, which is useful, for example, for meteotsunamis. As well, other services are using, providing near real time for operational purposes. So, regarding the second question, what can we say using this database, these data sets? In Europe, we have one of the regions that is best monitored worldwide in terms of coastal sea level from both altimetry and tide gauges. So there are some thousands of tide gauge extensions, for example, that can provide information on long-term sea level changes. If we are interested in mean sea level, and perhaps we can say that, let's say we plot the centennial scale changes in sea level from the tide gauges. The first thing we see is the well-known vertical and motion pattern associated to the glacial isostatic adjustment that was discussed also before because of the relative sea level change that I just mentioned. If we want to remove this part using some of the products that are available for vertical and motion and quantify which are the changes in the oceanic part, then what we get is some kind of the so-called stereodynamic signal in the long term. And we can do the same when we use the high-frequency sea levels from the tide gauges to look, for example, at the extremes. These are very useful if we use a metric like the one that has been discussed by Michalis in terms of, let's say, return levels. The tide gauges are very useful to identify which are the hotspots, the regions with the strongest sea level extremes, where we can expect the most important damages, for example. In the case of the Mediterranean Sea, well, we are in one of these hotspots, it's in the northern Adriatic.
Perfect. Thank you for that Very nice summary, Marta. And we can come back to that. We can come back to that as well. Okay, I'm going to move on to my next speaker, or panelist rather. That's Matt Palmer. And my opening question for you is about data availability. You worked with the recent 6th report from the IPCC on the sea level chapter. And my question is about data availability from that. And what are the main considerations when you take that and start applying it on a local level?
Okay, thanks, Matt. So, yeah, my name is Matthew Palmer. I work at the Met Office Hadley Centre in the UK and also at the University of Bristol. So I lead the sea level research at the Met Office Hadley Centre, and I led the sea level projections for the latest round of UK national assessments. I was also a lead author on the latest IPCC 6th assessment report, the Working Group 1 part of that, and had some involvement in the projections there. So in terms of the data availability, so it was interesting to hear the results of the survey that Jose presented earlier. I'd say that we're in a good place now in terms of the availability of the sea level projection data for AR6. So one of the best online tools that's available has been created in partnership with NASA. So if you do a search for NASA sea level projection tool, you'll find a very nice kind of web interface where there's a map presentation, and it's a point and click type of interface where you have access to site-specific sea level projections for a number of SSP climate change scenarios, and the time horizon for those projections is all the way to 2150. So it has a very nice kind of user interface. You can get not only the total sea level projections, but all of the various different components that go into those sea level projections, and as well as the likely range projections, which kind of Roderik discussed in his presentation. There are also some of these high impact but low likelihood type scenarios. So these are the more extreme possible kind of sea level scenarios available. So I'd encourage everyone to take a look at that. The second part of the question was about, where would you start with a regional analysis? So I mean, I think that so the AR6 sea level projections are really there as a starting point for considering what sea level rise might mean for your location of interest. I should quickly add that it covers the whole of Europe, so that it really does cover the whole spatial domain of interest to the Knowledge Hub. I think, following on from what Marta was saying, that it's very important to understand locally what drives the sea level variations that you see. There may be processes at play which are not represented within those projections, so that could be additional vertical land motion processes. That could be drivers of extremes which aren't represented in those sea level projections. Those sea level projections are really just giving us the mean water level over time. They also don't represent things like natural variability. So we know that in reality, the sea level rise that we see will be some combination of the natural climatic variations kind of superimposed on this more kind of sustained rise, which we see in the observations. So I think they're a really good starting point, but I think it's really a combination of observations, of understanding what's driving those local process, what the local driving processes are, and then bringing in some of those other factors alongside those sea level projections would be my standpoint. Thank you.
Good. Thank you, Matt. Okay, moving one along, we have Florence Corleone. And my question here is actually going into the past, deep into the past, about paleo observations and paleo observations of ice sheets, and really what's the relevance of those for future sea level in Europe. So thank you, Florence.
Thanks, Matthew. So I'm Florence Corleone from the National Institute of Oceanography and Applied Geophysics here in Italy. I'm a paleoglaciologist and a paleoclimatologist, a modeler. So I am also a co-chief officer of the Scientific Committee on Antarctic Research program INSTANT that focuses on instability and thresholds in Antarctica and the contribution of Antarctica to sea level rise. So going directly to this question, Matthew, I think what is really important to understand is that those instabilities, those dynamical instabilities, are triggered by very short-term effects. Could be ocean warmings, in addition to surface mass balance issues at the surface of the ice sheets. But the effect is really on the long term, because it's about a couple to 3, 4, 5 centuries in the future. What is really important is that in the paleo records around Antarctica, we have some evidence of that. So that's why we say this time scale is about 2 to 3 centuries, because in some sectors of Antarctica, we were able to date those instabilities. So we know that in the past it happened. What is really interesting is that in the past it happened under different climatic contexts, even with very low CO2 concentration, which means that CO2 perhaps is not the main driver of those instabilities, but ocean warming certainly is. The thing that paleo record cannot tell exactly is what is the tipping point in terms of ocean temperature that triggers those instabilities, because this is a coupled process with atmospheric processes, of course, and snowfall on the top of the ice sheets, which means that in different climatic contexts, the tipping point is also different. But we know, because of the geological record, that this happened in the past. So this is for sure that this will also happen in our future. I think that, as Sylvie said at the beginning of the conference here, that we are committing on a multi-generation level for sea level rise. Okay, this is not something we can avoid, and this is because of the large capacity of the ice sheets that absorbs the heat. So even if we stop warming right now, it will take a long time for the ice sheet to release the heat in terms of melting. So if we stop warming our system right now, ice sheet and glaciers will still continue to melt in the future for a few centuries to a few millennia. Okay, so that's something we cannot avoid. So that's really an important aspect. And I would say the importance of the long-term projections is that, first of all, we don't have enough climatic inputs that are realistic enough to really make very long-term projection, which adds on the uncertainty that we have in projecting ice sheet melting on the very long term in the future. And the long term really allows us, as Roderik said in his talk, to make the difference in the efficiency of our environmental policy. Only after the end of the 21st century, we definitely see how the scenario diverge, and IPCC could not rule out really the low confidence level because of the existence of those paleoclimatic records that make sure that those instabilities happen. So this is not science fiction.
Thank you, Florence, for bringing the past into the future there. That was very nice. Our final panelist is Jason Lowe. He's joining us digitally. Hello, Jason. Can you hear me?
Hi, yeah. Am I coming through loud and clear?
Sorry?
Can you hear me as well?
Oh, yes. Sorry. We can hear you. We can hear you loud and clear. Thank you very much for joining us. You work in the UK. You work with climate services. Climate services are about bringing sea level information from research down to decision making and adaptation and mitigation. Can you tell us a little bit about your work with that in the UK and what we can learn from that?
Yes, of course. So I work for the UK Met Office. I'm a principal fellow and head of climate services for government. And I've had an interest in sea level rise for 20 years now. I work and represent the University of Leeds. When we think about climate services, we often use this term, users or policymakers. And the first thing, it's really important to realize this is not one homogeneous group. It's subdivided. And each of those user communities has a different need. So if we're talking to central government, there will be particular questions and particular ways they like to receive information. They're not as focused on data, they're more focused on derived knowledge. We might also look at regulators. So in the UK, the Environment Agency and also the Office for Nuclear Regulation. have strong interests in sea level rise. Here, the need is to translate the sea level information into really quite simple forms that can be used for guidance and regulation for a much wider group of people who need to follow those planning limits. Then we have a range of practitioners, often engineering consultancies, who really focus much more on requiring data. They're very data literate, and they'll typically take that data and include it in their own models and analysis. We should also not forget the role of interested citizens. Now, in some cases, this is just an intellectual curiosity. In many cases, it's because those local citizens have an issue that relates to the coast, and they want to be informed and take part in a debate. The type of information we provide really differs depending on the use. If we're focusing on mitigation, then the link to the underlying emission scenario is particularly important. Also, whether we're passing a tipping point of some form, be it reversibility, irreversibility, or moving us towards an acceleration or an abrupt change. When we think about adaptation, the type of information depends on where the user is on their adaptation journey. And in some cases, it's initially about raising awareness or helping, for instance, a sustainability officer in a local council build a case for funding to look at this in more detail. At the other end of the scale, it's somebody actually making a decision. And here, typically, we're asked to be able to bound the problem and bring in uncertainty. But again, the type of information depends on the decision and the decision frame. If somebody is looking at flexible adaptation pathways, typically they will want to understand the likely sea level range, but they will also be very interested in high end and what options they should not rule out. Finally, I wanted to sort of say, how do we go about delivering it? Really the second part of the question. So a lot of the delivery is still scientist to user community direct interaction. When that happens, it's really important to think about good principles of co-development and make sure the relationship is balanced, because ultimately the user knows more about their particular issue than we do as sea level scientists. Increasingly, there is a role for boundary organizations like MSIP in the UK, and I think the Knowledge Hub plays a role of a new boundary organization that can specialize in the translation from the science to the user community and back again with feedback. Finally, we also need to recognize that many practitioners act as amplifiers and help us get the science to impact a much greater range of people through adaptation decisions.
Thank you so much, Jason, for that nice summary there. And so true that there's such a broad range of users with different needs, and this is a dialogue that goes back and forth. Okay, so those were the opening questions. We can move it on now into a bit of a Q&A. So if anyone, please, if you have a question, go up to the microphone and ask. You're never gonna, some of you will never ever probably encounter, again, such a concentration of sea level scientists. So now is your opportunity. Squeeze out from the middle row and head up and ask a question. Just go for it. Just go up to the mic and introduce yourself and put your question.
Hi, my name is Quiran Lodder. I work at the Ministry of Infrastructure and Water Management in the Netherlands. One of the questions was inspired by Roderik's talk, but it's actually in many other talks as well. I would like to hear from you what you would like, how you would like the AR1 for the GPI to be used. Because many of us said, okay, we're going to use the IPCC reports. And I would like to hear, so what you hope to add to that and how you hope we use it. I was inspired by Roderik, but maybe Matthew was touching upon similar issues as well.
Who would like to tackle that?
Do you want to start, Roderik, or shall I say some words?
Start.
Okay, I mean, so I think one of the difficulties or one of the challenges that we sometimes have when we want to work as a larger community is if there's a number of different products out there providing sea level projections, which one of those products do we choose? I think there's something to be said for having common benchmarks, common yardsticks, so we know, if there's two kind of countries, assessing their risk to sea level rise, it's kind of helpful to have, as I say, common benchmarks. And I would encourage the community to always at least have visibility and traceability to the AR6 projections as a means of doing that. Having said that, of course, because any risk assessment or any user decision needs to be kind of supported by a range of kind of information, and I don't think we can be too kind of prescriptive. I think we need the diversity in the products that are available for that, and I do support Roderik's view that really multiple lines of evidence is one of the ways to bring a bit of stability to that science. He talked about the need to refresh sea level projections. We find that in the UK there's a bit of a tension between, about how long you wait for that process. You can't update the projections too regularly. It becomes problematic in itself if that, if those things are moving a bit. So I think, as I say, I would encourage people to use the AR6 as a yardstick, so we all know where we are, but there has to be flexibility to draw on other sources, and I'll stop there and see what Roderik has to say.
Well, I think I largely agree with what you're saying. I think the yardstick idea is a very good one. There has been a time that I thought that there was only place for one yardstick, but I think I changed mind over time, over the last 10 years, I think, and there are different views, and I think it's worthwhile to consider those different views and to go into the details on why they differ, because that brings us farther as a community, I think, and we can discuss in detail afterwards what these differences are. And I think then it's up to the stakeholder on what he prefers to use in the end. I mean, as scientists, we cannot be prescriptive on what you should use and argue that this is the only yardstick which is around and that is what you should use.
Thank you, Roderik. I also see that Jason has got his hand up and would like to say something. So go ahead, Jason.
So if you take the IPCC and also Roderik's talk, those are two storylines. It's not that one of those is right and the other's wrong. It's that they make different assumptions. And that's really quite useful. So if a user, for instance, is following a process of robust decision-making, it's actually easy to incorporate that diversity into the decision-making process. Further, I think there are some really clear differences between those two storylines that relate to the confidence in the assumptions around some of the particular terms. And it's possible to have a dialogue with some of the more advanced users over their risk appetite and link the particular components and the confidence in them to that risk appetite. So it helps create a dialogue, having the diversity of storylines, rather than hinder it, would be my hypothesis.
Thank you. Do we have another question?
Yeah. My name is Nina Gardner, and I'm teaching business and human rights at Johns Hopkins SAIS and advising with a group called Adaptation Leader. And I have a more business-oriented question for you, because all of you are scientists and modelers, and I'm definitely not. But how many of you are, because obviously you have some very important data on your hands, how many of you are really working with the policy elements of your governments? We have Europeans, we have the UK, in terms of getting companies to report on their adaptation risk, because I work with investors, and investors need to push companies to start reporting on this, because we know that, I mean, these companies have a lot of money, and they are the ones who really are in the front lines, and are you talking to them? Because I think if these companies are not reporting out, then investors won't know whether these companies are actually doing what they have to do to mitigate these risks. In the United States and around the world in general, we're mostly talking about mitigation, but companies are not reporting on adaptation. So I'm wondering if you're talking to the policy people and the reporting people like EFRAG.
Would anyone like to have a go at tackling that one about the involvement of the private sector and the investment?
Well, I was going to volunteer Jason. I can see he's just raised his hand. I think he's probably better placed than me to talk about the UK situation.
Go ahead, Jason.
I'll have a go. Yeah. I think, firstly, this doesn't only relate to sea level rise. It relates to other climate stresses and other perils as well. So a number of us, Matt included, do talk directly to government. We talk typically to analysts, in our case, in a department called BASE that focuses on business, energy and climate change, and also DEFRA, which is responsible for managing the risks facing the UK from climate change. And that includes the risks to the private sector. So there's a government link. Secondly, I think there's a regulator link. And I think as a community, we do talk to regulators, but I don't think we talk to regulators enough. We need to have clearer guidance. In terms of talking directly to the private sector, I've had some experience of that recently through a project called the Centre for Greening Finance and Investments. And one thing we're learning there is, again, there's a very wide spectrum of some organisations, and I know pension funds often fall into this category, that are really only starting to consider adaptation. Other organisations, say the insurers and reinsurers, they are much further along the line, and so we are able to place some of the more recent climate results. There is an issue of what horizon many organisations think on, and when they allow for depreciating future assets and investment decisions, it's sometimes quite difficult to get them to think beyond the next 1 year or the next 5 years, and that's something that I'd be really interested in hearing your view about.
Thank you, Jason. Michalis, would you like to say something as well?
Yeah, if I may add something, and I have to be very careful because I shouldn't talk about policy as being part of the European Commission. We are not allowed to express opinions about that, but I think that the first step would be to know what are the actual risks. And already we have trouble to know what is the actual cost of extreme events, because it's difficult to get data from insurance companies, etc. So I think first we should try to focus in this first step to have input of data and then output. Then about adaptation, I think it's a challenging thing to talk about individual actions towards adaptation, because I believe adaptation has a lot about how we manage our water, how we manage our coastline, how we want to have our beaches being, or in general the coastal zone in general. This is a political topic. So if strong actors start to take measures and form, let's say, common assets that belong to everybody, then it can have strange results. So, for example, when we talk about sandy beaches and erosion, there is the classic problem that you have some very expensive houses in front of a beach. Maybe to protect these sandy beaches, you have to build a wall or a dike that will result in erosion in adjacent areas. And, but for these protection measures, everybody will pay taxes. So everybody pays taxes to protect the house of some rich or important people or whatever. And, but all the other societies, they are going to use a common good, which is sandy beach. So it's a political process that I think has to be regulated, and then comes the challenge. Everybody has his political views about regulation is good or not good, I think it's a complex topic, and I believe that actions like this report and everything we do would be useful to start this discussion, to raise awareness in the society. I think that would be, let's say, our main hope would be to try to start this discussion as early as possible, hoping that we manage to save something and not result in a completely concrete coastline in 20 years when the first storm comes and people start to die, and etc.
Thank you, Michalis. I see there's some other people who want to ask questions, so let's come forward and tell us who you are and ask your question.
Okay, so my name is Marco Ansidei. I'm from INGV, Rome, Italy, and I'm the coordinator of Save Met Cost 2 project funded by the European Union. This is not a question, but just a comment that what we need is the relative SLR projections. So what we need to assess for risk assessment, the contribution of land subsidence to provide detailed scenarios of sea level rise along the coast of the Mediterranean as well as in the other, beyond this border. So I think it's very important because, for example, what we know in Venice, what's happening in Venice is different. What is happening in some other part in other areas. So this is my comment.
Very good. Does anyone want to respond to that comment quickly?
I mean, I can respond quickly. I mean, I agree with you. I think it's really important to have a good understanding of those local processes, and I think that's where these local assessments can go beyond, the sort of information that's put out as part of IPCC AR6 that can't do the type of detailed analysis that's really needed. I should say that there are estimates of local vertical land motion, projections of vertical land motion within the AR6 projections, but I think really, a close look needs to be, you need to bring to bear as much of the local knowledge and much of the local information as you possibly can when you're making an assessment of what changes we might see in future. But I agree with you, thanks.
Thank you. Okay.
Very briefly, in that respect, there is not enough, in my opinion, observations of vertical land motion. The network should be enlarged.
Thank you, Marta. And Angélique?
Yeah, perhaps on the data themselves, we recently set up in Copernicus a service dedicated to vertical land motion, so that could be useful, although it might not be at the very, very local scale. And regarding projections, I think that's where also local knowledge would come into play, because that also depends largely on decisions that could be made at the local scale, such that we saw that for Venice or for other cities where they stopped pumping in aquifers and they reduced the subsidence subsequently. So depending on human decisions, we can also largely change the projection of relative sea level rise at a local scale.
Right, yeah, we have this European ground motion service, right, which is including INSAR and gives very detailed view across Europe of vertical land motion. We have an online question. Do you want to read it out?
Thank you very much, Matt. And thank you very much to all the panelists. We do have a lot of questions online. I'm just lending my voice here. But I wanted just to say briefly that if there is not enough time to address all of the questions, please feel encouraged to also go on the Slido and type in your answers to these questions. But I do have one specific question for Angélique. Angélique, you showed very nicely the propagation of global sources to local impacts, including dynamic downscaling. This knowledge hub on sea level rise is also about co-design, so in a way it's propagation sort of the other way around. Do you think that the scientific and the communication tools are in place for this to happen, and which tools do you think could be implemented?
Well, I think that co-design for more local sea level information is really being developed right now. The Knowledge Hub is an example of that, where we are in the scoping process actually for the assessment report, even right here, right now, to know what people need in terms of information for adaptation. It was also the case at other conferences, such as the WCRP conference that we had in Singapore in July, where it was also bridging practitioners and scientists together to better understand what they need. So that's part of the co-design process. And even in research project, like European project, for instance, co-design is more and more being developed to, again, better address what people need in the end to use this scientific information.
Great question and great answer. Okay, we started around 10 minutes late, so we are going to have to start wrapping up now. But very quickly, I want to do a little fun thing. I want to go through our panelists very quickly, and you've got 10 seconds each. 10 seconds to give us a take-home message. Go, Marta.
Okay. In my opinion, observations are essential for understanding and quantifying sea level and understanding the drivers, which is the only way to anticipate how sea level will change, and this is what it's all about. So maintaining observational networks is very relevant.
Thank you so much. Let's go on to Matt.
So my 10-second thing is for everyone to go and look at this NASA sea level projection tool and go and play with it and see what you can find out.
Great. On to Florence.
Yeah, so deep paleo records definitely tells us that low confidence, high-end scenarios are not science fiction.
Very good. And finally, Jason, what's your take-home message for us? 10 seconds.
Co-development, really important. Uncertainty can be managed, but we need to understand the confidence in it, and we need to look more at the information beyond 2100, especially up to 22 and 2300.
Super. Thank you very much. And that concludes our session. I would just like to say a big thank you to the organizers, all our keynote speakers, and the panelists. And there's a little bit more to say maybe on the practicalities, but thank you. We can give them all a round of applause, can't we?